Hello, this is our 4090 final project for QSEP Serbia's case study.
Van Gemert.
I'm Jesse Odhiambo.
Hey, I'm Tirani Oyunusi.
I'm Kevin Brim.
The geometry of our CubeSat is 100 by 100 by 340.5 millimeters. The mass properties is the total mass is 4.9 kg. Here are all of our moments of inertia, and that's our center of mass down below. For the orbit, it's 500-kilometer altitude, sun-synchronous orbit. Mean local time is setting node, it's 9 o'clock. Initial POC is June 1st, 2025, 12 o'clock UTC. And the length study of the case is 3 orbits. Here's all the data we inputted into the orbit simulator to obtain all of our data.
All right, so for task one, our objective was to determine the spacecraft's attitude that maximizes its power production, and then plot the time evolution of said attitude using both quaternions and Euler angles. For our approach, we downloaded the most recent version of the OS thanks to Professor Maja on the last slide, inputted our parameters, ran the simulator, got our data, and there we got a reference frame axes map file. And there we got our RBI, and using the inclination equation for sun-synchronous orbit in the user guide, we found the Euler angles psi, theta, and phi. Then we found our quaternions utilizing Shepard's method learned in lecture, and we finally plotted our time evolutions for both the Euler angles and the quaternions. Next slide, please. So these are some of the equations we use. As we see some of the RBI equations from lecture and also the inclination equation from the user guide. Next slide, please. And yeah, we see our Euler angle time evolution plots. We see phi, psi, and theta on this one. And then on the next slide, we're going to see our quaternion plots right here, QO, Q1, Q2, and Q3. Next slide, please.
All right, for task two, we computed the total external torque necessary to maintain the ideal sun pointing altitude, and then plotted this required torque profile over time. We approached this by retrieving the quaternions from task one, then used the finite difference equations to approximate the time derivatives. Then using inverse kinematics, we found the time history of the angular velocity. Then by repeating the finite difference procedure, we were able to calculate the time history of the external torque needed to keep the desired attitude. We also worth noting that we discarded the first few and last few points due to numerical instabilities. So these are some of the critical equations we used. And here are the results. And as you can see, the different components plotted over time, and then the normalized moment versus time, and they hold a sinusoidal trend as we plotted them over time.
All right, our task three was our disturbance torque modeling. First up, we have our solar radiation pressure torque. To find this, we determine the areas, centroid, and distance from the center of mass for each of the spacecraft panels. Then we use the sun direction vector with the surface normal to determine whether the surface receives sunlight. Then we computed our SRP force, and then from the force, we computed the SRP torque. And on the right is critical equations to do that. Next slide, please. And here we have our SRP moment components versus time and total SRP moment versus time. We see that it follows the expected trend of being sort of on and off, on when it is in sunlight and off when it is in sunlight. In umbra, excuse me. And next up, we have our aerodynamic drag torque. To find this, we use the same centroids and all that from the previous step and the velocity direction vector to determine whether the surface is exposed to flow. And then we computed the aero force and followed by the aero torque, similar to SRP, with critical equations on the right again. Next slide, please. And here we have our aero moment components versus time and the total aero moment versus time. Both follow a sinusoidal trend throughout the whole simulation.
Our third disturbance torque is gravity gradient. We linearized the equation motions derived in lectures 2021, pulled the RC, created a skew matrix, solving for gravity gradient torque components, and using the gravity gradient moment equation, calculate the vector magnitude of the total gravity gradient torque, and then squeezed and then plotted. Here are the critical equations we used. And here are the graphs. So this shows the X, Y, and Z moment for gravity gradient. It is very sinusoidal. And then on the right, we have our total over time, which is continued to be sinusoidal. Our final disturbance torque, residual magnetic dipole torque. obtained by spacecraft's magnitude residual dipole and Earth's magnitude field BRF. We have to convert the magnitude field to nanotesla to Weber meter squared and calculate the spacecraft MRD magnitude and the Earth's magnetic field vector magnitude for each point, and the residual magnetic dipole is found across product of the space magnetic residual dipole and the Earth's magnetic field. Here is original, here's our graphs, and this is the RMD torque with the X, Y, and Z, which just seems to be very sinusoidal. And then for the total, it looks sort of sinusoidal, but it's due to it being the averages, it doesn't completely follow it. And this is our desired control torque. As you can see, they all are pretty much sinusoidal, and they follow the lines very quickly. And this is what our desired torque for our vehicle will be.
All right, so for task 5, the Cerberus utilizes 3 magnetorquers, and our objective was to determine the feasible control torque that these magnetorquers can produce. In addition, we also wanted to make sure that the corresponding dipole moment is in the constraints of our given maximum dipole moment constraints, as you see in the bottom right corner of the slide. We utilize these 2 equations right here. Next slide, please. And yeah, we see our control dipole moment was in fact in range of our given constraints, very much so. You see the X, Y, and Z control dipole moments in it. On the next slide, if we can go to the next slide, you can actually see a zoomed in view of that control dipole moment versus time. In addition, we see our feasible control torque versus time on the right. Next slide, please. Yeah, so in addition, we also have some really cool plots showing the desired versus our feasible control torques versus time. You see our feasible traces are desired very well, aside for a few off moments just due to some interference. But yeah, you see our total desired and feasible control torque versus time on the bottom right. And we can see its success. Next slide, please.
All right, so in task 6, we did our attitude simulation and pointing accuracy assessment. We simulated the spacecraft's rotation motion using the feasible torque calculated in task 5. And then to evaluate the accuracy of the sun pointing altitude, we computed the angle between the body fixed panel normal vector and the sun vector. Based on our requirements, the spacecraft must maintain sun pointing accuracy within 5%, and any deviation beyond this must be reported. Next slide, please. So our accuracy assessment shows that due to the moments being so small, the feasible torque was able to control the spacecraft, and there's a very small change in the angle because of how high in altitude the spacecraft is. In conclusion, from our calculations, the spacecraft stays in the correct sun-facing orientation throughout the whole mission. Next slide.
Improvements on our accuracy. Alternative actuation. We can use attitude control thrusters to help, controlled moment gyroscope, and momentum wheels, which will also are very high speed and will provide smooth accuracy on our mission. And we also even use solar sails due to we not being control while in the umbra, due to there being no sun. Control strategies. We can use nutation dampers to be more precise, use magnetorquers at their maximum local magnetic field, be able to price and control before it goes into a space where it cannot be in control, and adding more magnetorquers for redundancy and for more control. And these will all devices and strategies will improve the success of the mission. And here is our references. Thank you.